First, I want to just say that this is a joint effort of a big team of people that I really enjoy working with in Austin. One of them needs to sit down. So let me give you a little overview. Before any of this is going to make sense, I need to tell you a little bit about the Hexagon DSP processor and what it looks like. And then I'm going to divide the actual work part into two sections, the initial porting work that we did, and then some of the more recent stuff we've been doing to improve the performance, and then talk about our future plans. So what is Hexagon? It is, the reason it's called Hexagon is because it's the 6th generation of DSPs that Qualcomm has produced. We initially internally called it QDSP6, so if I slip during the talk, I'm still sometimes in the habit of calling it QDSP6, but Hexagon is the marketing name for it. It's been used in a lot of products that Qualcomm ships. It's a core that's been integrated into chips that go into cell phones, base stations, data cards. It's used in our HSPA Plus and LTE modems. It's also been used in femto cells. It's a very general purpose, when we've worked very hard to make it easy to program, to make it very powerful. It's a really high throughput, low energy processor, and I'll talk about some of the ways we get it to be that way. So there are certain things, if you want to be a DSP, there are certain things you have to do well. You have to be good at FFTs, dot products, things like that. So some of the first design parameters we had, we wanted to have a very wide multiply accumulate engine. We have support for dual 64-bit loads and stores. You know, we've always been looking at the competitive DSPs in the industry, making sure that our performance is as good as or better than those. There are certain types that you have to call yourself a DSP, you know, fractional types, complex types. We also have support for saturation and rounding. Unlike some DSPs, we don't do that with modes. They're actually, those operations are encoded into certain instructions. And we have 3 types of parallelism on the machine. It's multi-threaded, sort of beyond the scope of this talk to go into how it's multi-threaded, but it's an interesting way to keep the throughput up. It's the part that I want to emphasize here is the fact that it's VLIW, and it has up to 4 instructions in parallel, and it also has support for SIMD. We can do up to 64-bit vectors, either of 8 8s or 4 16s or 2 32-bit operations in the same instruction. Okay, so when we started the project many years ago, we realized that the uses of DSPs and the amount of code that's running on cell phones in general is just growing exponentially. And we realized that this DSP needs to have a lot of the features that are traditionally found in CPUs. They need to be easy to program. They need to be able to run a high-level operating system as well as a real-time operating system. So we worked very hard. I'll never forget one of the early meetings I was in when I first joined the company. I don't even remember the topic, but I made a comment to the effect of, well, that's easy. The software can do that. And all the people in the room looked at me sort of strangely, and they said, no, that's firmware. And I looked at them kind of strangely, and I said, what's the difference? So the difference is sort of historical within the company. I mentioned that this is the 6th generation of DSPs. All the previous generations had been programmed all in assembly language. There was no C compiler to use on these DSPs. So there was a big organization of people who programmed DSPs in assembly code, and that code was called firmware. And then there was another big organization of people that wrote C code and ran it on an ARM, and those were called software developers. So enter a DSP that has a good C compiler, and you've got the opportunity now for DSP programmers to write C code, and then you've got the ability for C programmers to write DSP code, and it's sort of like cats and dogs living together. It's been an interesting set of years. So we worked hard to kind of serve both of those communities within the company, both the traditional DSP and the traditional CPU C programmers. So the compiler that we had for years was GCC, and we'd worked over several years to tune GCC and improve the performance of it and make it do a really good job generating code. So let's see, where was I? So this thing looks a lot like a CPU as well as a DSP. It has precise exceptions, it has an MMU, and it also has hardware support for virtual machines. So this famous high-level operating system I mentioned, it actually runs on top of a hypervisor, and we can run multiple operating systems at the same time. So, this is not your grandfather's DSP. It's a really, really impressive. We're really proud of the work that we've done in the software environment and the number of products that it's been used in. All right, so this gives you an example of what the code looks like. If you were in the OpenCL talk a little while ago, the guy, he talked about packetization. And it kind of threw me for a loop because we talk about packetization in terms of forming packets for a VLIW instruction. So the syntax here, if you see the curly brace, that indicates a VLIW packet. And the semantics are what they would be with a traditional VLIW, where at the beginning of the cycle, you read the register operands, then of all the instructions, you do the computation and then you write them back, which is not necessarily the same as if you execute them in sequential order. For example, if I say R0 equals R1 and R1 equals R0 in the same packet, that's actually a swap, which is a different behavior than if you execute them sequentially. Okay, so the syntax of these instructions is somewhat kind of pigeon C code-like. Whatever's on the left side of the equal sign is an output or a result, and then on the right-hand side is some operation. So this is the syntax for a register pair, R1716. So that's a 64-bit quantity, and it's doing a memory load from wherever R0 points, and then a post increment with a value that's held in that other register there. And then in parallel to that, we can do a store, again 64 bits. And then the red instruction there is a complex multiply with a shift by 1 and a round and a saturate. And so over here's a picture of what that does. Then the fourth instruction here is vector add of half words. So effectively, what that's doing is doing two complex adds in one instruction. And then this little tag here is a special tag that goes into the encoding of the whole overall packet that says this is the end of a hardware loop. So what that's going to do, it's going to decrement the count, do a compare with 0, and then jump back to the top of the loop if you're not done. So if you do the math, depending on how you count, you get about 29 sort of typical RISC instructions in one cycle that this is executing. And this is actually the inner loop of an FFT for our processor. All right, so let's talk about the initial porting work that we did. We knew that we had a GCC compiler, and we knew it was out of gas for a couple of reasons. We'd done a lot of work to push the performance of it, but to get really to the next level, we weren't sure GCC was going to get us there. We also knew that things were coming down the pipe in the cell phone business with heterogeneous computing and managed languages and just-in-time compilation and some of those things that we'd want to be able to do that obviously GCC doesn't play in that space. So our initial porting work, I'll kind of characterize it as rapid prototyping. So we had two engineers, one of whom had seen LLVM in a past life, and another one who had never seen LLVM before, worked on this. It took them 23 days to initially get the LLVM backend working. And by working, what I mean is passing our benchmark suite, which has about 15 DSP benchmarks. Some of the embassy codes, an MP3 decoder, an H.264 decoder, things like that. So once we got it actually passing those tests, we worked on performance. We wanted to see how quickly we could get the performance up. And at the end of about 107 days, we were at 87%. Now, before you get too excited, let me just point out we were able to leverage all the other infrastructure that we had, like the test harness, the assembler, and the linker. So we're really only focused here on the compiler. So we were really happy with those results. It really pointed to the promise of LLVM. It's easy to use. It's very well documented. It's very carefully engineered, very modular. So we liked it. We thought it was a good thing to use to move forward. So here's the timeline that we have. So these are days across the bottom, and then the relative performance of the code on the vertical scale. So like we said, the 23 days here is that little section. Then the biggest single thing that we did to improve the performance was right here to forming the VLIW packets. And this was really a post-pass at the end to where we looked at the final schedule and said what instructions can be placed in the same cycle and form packets around those. So as you might imagine, if you're an aficionado of scheduling or instruction level parallelism, that's a kind of a suboptimal way to form packets. But for this exercise, sort of rapid prototyping, it worked, and that was the single biggest jump. Then we had several other things. We looked at the code that was being generated and found lots of things that could be improved. Not really at the level of adding new passes or anything, but like identifying new instruction patterns and so forth. And I don't think if you've worked in compilers for a while, I don't think the shape of this curve is going to be any surprise to anybody. You start off and there's a lot of low-hanging fruit and things that are easy to implement and give you big jumps in performance, but as you get towards the end, it takes a lot more work to get the performance improved, and we certainly saw that here. Okay, so at the end of this is transition time. We wanted to switch over. We want to make LLVM the production compiler for our core. Well, a couple of things happened in parallel to this work. The first one was that the team working on GCC delivered a new version of GCC. That moved the bar up about 10% in performance. The other thing that happened was a new version of the core was released, and a lot of work had gone into GCC to take advantage of the new features of that core. So that moved the bar up about another 5%. So now we're looking at a bigger hill to climb. Instead of being 86% of the performance, we're looking at about 72% of the performance of GCC. So we started applying more people to it. We worked hard. The first thing we did was we took our existing compiler test suite, which, depending on how you count, has about 100,000 tests in it, and we can run it over a variety of configurations, and we've got an infrastructure that does it in parallel and things like that. Initially, I have to say, this is the first time in my career that I've ever seen a pass rate at 0 lower than the pass rate at 03. So, usually you think, oh, 03, you got all these fancy optimizations and, NP complete problems you have to solve and corner cases of this and that. And there's a lot more chance for bugs with an 03 compilation. But if you sit back and think about it, the initial prototyping was really focused on benchmarking, and all the work had gone into building with 03 and looking at the code patterns that you get to the back end when you compile for 03. So there were missing patterns. There were corner cases in things like the ABI and C++ exception handling that we had to fix. And we pretty quickly got the pass rate up to about 98%. And the majority, I'll say, of the remaining bugs are what I'll call corner cases in the C++ front end. We've also been working on performance. I'll talk more about that. I got an email last night from the guys back in Austin that we're now at 90% of the performance of GCC. So we went from 72% to 90%. We're still working heavily to try to get that up above 100%. Okay, so now I'm going to talk about some of the things that we did along the way to get from that 72 to the 90% performance. So as you might imagine, since we are a VLIW machine, one of the most important things we have to think about is instruction scheduling. It's very important to make the optimal use and get 4 instructions that can execute in parallel. Okay, so we originally wrote that packetizer, like I said, was really a post-pass that looked at already allocated, already scheduled code and just tried to form packets. It looked at what instructions were legal, both semantically and based on the machine resource constraints could be put together. And we found one of our benchmarks, we found sort of a pathological test case that I'll characterize it as a little oversimplification, but let's say I have a load and then a mathematical operation and then a store, and then another load, a mathematical operation, and a store. So a sequence of that, they're all provably don't overlap in memory, but the scheduler wasn't doing anything to look at the alias information. So it essentially linearized that section of code. So we said, oh, okay, great. We'll go and we'll add knowledge of alias information into the instruction scheduler. So then what happened was all the loads floated to the top, all the mathematical operands were in the middle, and then all the stores floated to the bottom. Well, that didn't work too well either because it wasn't taking into account the machine resource constraints. We can do 2 loads or some combination of 2 loads and 2 stores in a cycle, but we can't do any more than that. So what we needed to do then was to teach the scheduler how to understand resource constraints, so that we'd do 2 loads, and then in parallel to that, do some mathematical operations, and then when it's ready, it can schedule stores. And so you get a much more efficient use of the machine pipeline when you take that into account into the scheduler. The other thing we looked at was the loop unroller. We noticed that the loop unroller in LLVM would only unroll loops whose trip counts were known at compile time. So we see a lot of codes, and for a VLIW machine particularly, it's important to unroll the loops. You give your scheduler a wider piece of code to deal with. You get a better chance to overlap instructions. You can also try to unroll to try to balance the pipeline so that the number of operations that you have matches the number of available resources on the machine. Excuse me. So we've seen both large improvements with this kind of work, and we've also seen some losses. There are times when you can unroll a loop, and then the scheduler gets more aggressive, and that causes the register allocator to spill, and the net result can be worse. But we have seen some pretty large improvements as well. So we think on the whole, it's a good thing. I think if we want to take it to the next level, we probably need some sort of target-specific information. So if you think about it for a second, different machines have different needs when they want to unroll a loop. So one of the things for us is we want to make sure we balance the resources on the machine. So let's say I have some loop with 2 loads in 1 store. Now, in our machine, you can do some combination of 2 of those. So I've got an imbalanced pipeline. I have to take 2 cycles to schedule that at least. But if I unroll it, now I've got 6 operations. That's evenly divisible by 2. So that's a better use of the pipeline. I'll also talk about this in a minute. We have hardware-controlled loops on our machine. So we don't get any benefit in terms of reducing the loop overhead of unrolling a loop. So I think different machines are going to have different needs and want to pick different unroll factors for different reasons of different loops. So I know this is possibly controversial. It might violate some of the purity of the design to have machine-dependent information in a machine-independent part of the compiler, but I think if you do it judiciously and you make it based on the feature of the machine versus are you an x86 or not, those types of things I think can benefit greatly. And this patch I'll mention is currently under review on the commits list. Okay, then there was a whole bunch of miscellaneous things that we did with the compiler. Again, if you've worked on this type of work for a long time, you know that it can be death by 1,000 paper cuts. This is sort of the flat part of the curve where you have to do a lot of things, and each one gives you a little bit of performance along the way. So I'll talk about hardware loop support in a minute. If you remember the example that I showed before, the core supports post-increment addressing mode. So we did some work on that. We're currently doing some work to tune the loop strength reducer, trying to get it to look at the totality of all the addressing computations within a loop and figure out what the best addressing mode for each one is. And our core actually supports 3 different types of addressing: base plus offset, post increment, and base plus index. So depending on a lot of different factors and the combinations and the relationships between the memory accesses in a loop, you want to choose different addressing modes depending on lots of different criteria. And then I mentioned the new version of the core that was released. So that introduced a whole bunch of new instruction combinations that we needed to add to the back end. There were more relaxed packet forming rules so that more different types of instructions can be run in the same cycle. And then sort of a general bucket called enhanced predication support, which is another feature that's really important to generate good code. We have a feature that's called .new, and what that means is instead of the normal semantics that I mentioned earlier where you read all the operands, you perform the operation, and then you write the result back all in the same packet, if you can specify certain operands to use the new version of the value. So in other words, more like sequential semantics. And in particular, like you can do compare and load and compare and jump in the same cycle rather than having to wait. So this is really good for control code where you're doing load, compare, branch idioms and things like that. And it's also one of the sort of, if you think about traditional VLIWs, this is one of the criticisms that people have is that, if you've got really sequential code, that there's nothing you can do in lots of branches and stuff. There's not much you can do, but we put a lot of work into making that kind of code run really efficiently on this core. All right, so let me talk about a hardware loop. So I've seen this on other processors, and it's always done with more or less the same way, but all the differences are in the details. So for us, we have two loops, two hardware loops, an inner and an outer, or 0 and 1. And each one has a start address and then a loop count. And then there's a special instruction that sets those up. So in this example, here's a fairly simple, benign piece of C code that does a loop, A plus equals B sub I. There's the label at the beginning. There's a load. You're subtracting 1 from the count. Then you're comparing that to 0. And then there's an example of this .new that I mentioned. And then you jump back to the beginning. So if you transform this loop 0 instruction puts the label at the beginning of the loop into the SA0. And then the value of R0 is the loop count goes into LC0. And then this little tag here at the end tells it to automatically decrement the counter and jump back to the beginning in every cycle. So as you can see, what we did was we got rid of this add, that compare, and then that branch, and we're just left with the memory load and then the add to accumulate into A. Okay? So quick pop quiz. What's wrong with this? Sorry? Well, A is a scalar, so it's kept in that register. So actually, the problem with this is the code didn't get any faster. Still two cycles per iteration, but this is sort of a, since it's such a simple loop, there's not much you could do. Now, you could software pipeline this, of course, and get it down to 1 cycle. But we have reduced the code size, and we've also reduced the amount of power that it takes to run this loop. So it's still a good thing to do. All right, so let's talk about some of the next steps that we see. We've been working on upstreaming our changes. To be honest, I think we held on to our changes too long. We should have been upstreaming them sooner. Eric is nodding. Forgive us. We're still learning. Hopefully we've learned our lesson the hard way. So I'll put in a plug. If there's anybody out there who is holding back changes, hasn't upstreamed them, get them up there. It's not that hard. Some of the other things we need to work on, code size reduction, always important for embedded processors. There's been some discussion on the dev list about how to represent VLIW packets in the back end. And I think there's a lot more discussion. I'll sort of throw out a few thoughts that would be nice to have as a way to represent a packet or any sort of opaque set of instructions that can be run through various parts of the back end. So, just for simplicity, think about the register allocator. It's got to be able to compute liveness and things like that, and insert spill code with these things. But you don't want it to have to understand what's going on inside of a packet. And you certainly don't want to have to rewrite it to say, okay, if this is a packet, then look inside of it and figure out what it does. So let's say we had some sort of a wrapper or a container that could hold a set of instructions. This could work for lots of things. It could work for inline ASM blocks. It could work for, say, a software pipeline loop or other types of special schedulers or allocators, and then allow other parts of the compiler not to have to know what's inside them, but can paste them together, can do register allocation, can schedule them within the other code instructions that it does know about, and things like that. So I think there's a lot of room that we should discuss, on the dev list about this. Another thing we want to look at is multi-basic block scheduling with Trojans and super blocks and hyperblocks and those sorts of things. We want to be able to unroll loops with multiple exits. And then improve the alias analysis. In particular, we've seen some issues with the type-based alias analysis, and understand it's on purpose that it's not as aggressive as it could be for fear of breaking people's code. But maybe under a flag or something like that, we can make that disambiguation more aggressive. And I talked a little bit about this earlier, exposing limited amounts of machine information to the optimizer. I think if you do it judiciously and generically, that it won't do too much to break down the purity of the design. And some of the things I think are key are limited places where it's important, not too gratuitously, and make it based on the feature of the processor you're targeting. So like which addressing modes or which unrolling factor is used. Not pound if target x86, else if target ARM, else if target Hexagon. That'll drive you crazy. But if you said pound if my target supports post increment, then somebody who wants to add a new target, well, they know exactly what to fill in there because they know what their target is. And then the last thing I want to say that we'd like to do is work on software pipelining, because that's a very important transformation for loops for VLIW machines. So with that, we'll open for questions. Sorry? Really? Yes. What time are we supposed to finish?
Like 15 minutes.
Okay. Yes.
So you mentioned the super blocks and hyper blocks,
Right.
right? LLVM IR, today they don't represent them automatically. So when we envision doing such transformation in front of the compiler, or what enhance the IR to do that?
That's a good question. Personally, I would vote for enhancing the IR.
Repeat the question. Can you repeat the question?
Oh, sorry. The question was, LLVM IR can't represent hyperblocks and superblocks, so where would I do it in some other place or within the existing place? So I would vote to extend the IR to support that, at least the back end IR. There was a question over there. Yes.
Yeah. And you said the first thing you did to improve it is you said, hey, I know that I'm going to make this thing called, packet, with really one instruction. And it's more like you already knew your rules for load, store, or whatnot. And you said, you got your biggest hit, but it looks like it's almost, that's already part of sort of going for optimization. So do you think, has that really hurt you, or how good of packagizing or increased throughput have you really gotten by doing it the way you've done it there? In other words,
So
theoretical, 100%, what are you really running the processor at? Is it, you're going to have a certain amount of holes.
Okay, so let me try to repeat that question. How good do we think we're doing based on the fact that we're forming the packets at the end of compilation? Is that your question? So I think there's a lot of room for improvement. The good thing is, yes, there's a lot of room for improvement, but it is going to require some changes into the representation. Like, can we form these packets early, like say before register allocation, and then have them live through the allocator, and then have say the post RA scheduler try to push some of the spill code into empty slots in the packets. Since we were initially in sort of rapid prototyping mode in the chart with the curve on it, we didn't want to go through and make major changes to the back-end infrastructure, so we chose to do it that way. And we've been working in little bits of ways to improve it since then. And then to take it really to the next level, I think we're going to have some conversations about how to represent these in the back end, form them early. Yes.
So you talk about schedule change. Did you know about this information? Are you writing a new schedule or are you making changes to the existing schedule?
Correct me if I'm wrong, we're making changes to the existing scheduler.
Currently, yes, but we probably will be enough force to writing a new scheduler, unlike the LLVM or register press, or even like VLIW scheduler altogether. Other patches coming? I'm sorry? Other patches for the patches are coming. First, our backend has to be merged in, right? And then we have to form patches and all of that. So you want to make sure those don't break on the patches. Oh, yeah.
Right. So like I mentioned, we had, and we've been, for whatever reason, too busy making changes. We're sort of behind in getting things upstream, so we're going to do it in some phases. The original back end is up on the review list now. The loop unroller's up there. Then after that, we'll do we'll try to upstream the packetizer, and then the changes to the scheduler, and eventually we'll get it all up. But we were afraid if we just dumped a whole bunch of code on the commits list, it would just be too much chaos. So we're trying to stage it, get reviews, and then get to stable points, and then put the rest of the stuff in. So we've got sort of a pipeline of things we want to push to the commits list. Yes, in the front.
So what do you say about how your relationship is with the GCC team?
It's very good. It's actually the same team. Sorry, the question was, what's the relationship with the GCC team? In the red shirt?
So it looks like that Hexagon is getting very close to the Italian identification, packaging, bundle. Do you feel, my question is, do you feel need for speculation to improve performance given that aliasing may not be as good? So do you feel need to improve performance, need for having speculation support in hardware?
So the question is, do we need speculation support in hardware?
Maybe also for optimization.
So speculation, given the market that we're in, which is devices that run on batteries, I don't know that we want to do stuff that uses extra power that may not actually result in a computation that's used. So maybe for another market, if this processor were used for something else, some other type of market, I think that might be a good idea. But in the market we're in, we're very conscious of power consumption, die area, as well as code size. So I don't see that coming in our processor. Yes.
My comment is instead of adding a machine-dependent feature into optimizer, for example, loop unrolling, can you consider splitting the loop optimizer in backend? Having two different loop unrolling. One is original and the second in the backend code generator that is fully machine-dependent. I mean, it's a commercial comparison I'm coming from.
Right.
It's the case, you have high-level loop optimizer, and then you have low-level loop optimizer.
Okay, so the question was, would we have another loop unroller in addition to the machine-independent one that is machine-dependent? I wouldn't rule that out. I think there are a lot of reasons to do loop unrolling in different places and with different constraints and things like that. Right. So then that's an engineering question. You've got duplicate code with presumably the same functionality, and can you share it and things like that. So I think you just have to do that kind of thing judiciously, I think. Yes.
Just a comment on this. LLVM is going to the point where we will be adding new optimizations. It will require a little bit more target information. We do have to, like for the vectorization, we'll have to know something about the target. So it hasn't happened in LLVM yet, but it's something that I think we have to be sensitive to capturing the information. It's not, doesn't mean the optimizer is going to link in the target library. We have to
Yes.
Performance difference GCC, do you know which ones are just missing fastest or which ones are actual differences in GCC versus LLVM?
So the question was, in the performance differences, is it structural differences or is it, I guess, minor things? Is that what? Missing optimizations. I think it's a combination of a lot of different things. You know, GCC itself has been, you know, tuned over, I don't know, what, 20, 25 years. And our back end for GCC has been tuned over 4 or 5 years. So you know, it's a matter of taking the time to catch them up. And I think there's some things that are sort of big ticket, like you know, we've talked a lot already about scheduling and how to do VLIW representations in the back end. And there's other sort of, you know, little minor tweaks as well that we can make. So it's a lot of things. There's no one. If there were a silver bullet, you know, that chart would have said 110% instead of 90%. So anything else? Let me get this guy.
I assume you're not shipping it to customers yet. What would be the cost or requirement to do maybe tool deploy GCC and LLVM product and then flow it over to an LLVM product to customers?
Good question. So when will it be ready to deploy to customers? The target that we've set for ourselves is actually a quote from one of our customers. He said it needs to be compellingly better. And so by that, I take that more specifically to mean that it needs to be better on their code in either performance or code size and not significantly worse in the other. So if it's, for example, if it's 2% faster and 5% bigger, that's not compellingly better. If it's 2% bigger and 10% faster, that's compelling. And I think that's the point where people are going to want to switch to it. So that's what our goal is, to make it compellingly better. Yes.
Last year, in the same conference, you mentioned that GPU and DLE are important for this type of processor, and I don't see today on your topic. Can you comment on this? Why DLE or GPN are they still important for Hexagon or not?
I believe they are important. The question was, is global value numbering and partial redundancy elimination important? I believe they are in in the sense that I believe they would improve the code. I'm more pragmatic, though, in that when we look at the code that's being generated by the compiler, that's not what jumps out at us, and that's not the stuff that we're seeing needs to be fixed right away. I think once we get past some of these other higher priority issues, yes, it will be important. Okay. All right, thank you.